Okay, this is take 3. I'm having problems this morning putting videos together. If you saw the previous video, which was the first problem under test of independence, you can tell I'm shaking. And on top of that, my coffee grinders burrs have fallen apart, so I'm beset with first world problems here today. I hope I can get through this. And this, in this case, is problem 2 of test of independence, which is up on the screen right now. You can see what it's about is a public opinion poll, surveyed 1,000 people, kept track of who was male, who was female, who was Republican, who was Democrat, who was independent, summarized all the data in a two-way contingency table with a row variable being voting preferences and a column variable being gender. And they want to ask the question, is there a relationship between how people vote and their gender, or are those two factors independent? And a test of independence is exactly for that application, as you'll see in just a second. So there's the data. Let me scoot to this screen because I want to go just as quickly as I can to the calculator to show how the calculator disposes of these problems. So this works. This test for independence is a disguised hypothesis test. It is a sister to goodness of fit. The two work a little bit alike, right? In the goodness of fit, you go to the under edit, you go to a list and fill up a list with the observed information, and you fill up a second list with the expected information. And then you go to test underneath statistics, chi-squared goodness of fit, and answer the questions there, and the answer gets spit out onto the floor. You have to jump back so it doesn't hit you in the foot. Pretty much the same thing for test of independence. You input the observed data. The calculator actually calculates the expected data for you. Unless you look, you will never even see the expected data, because you're then going to take that observed data, take it over to stats, go down and find chi-squared test, run through the questions there, and again the answers come spilling out. The one difference is that when you input data for test for independence, and this is only true of this test, you don't put it into lists, you put it into what is known as matrices. So a matrix, for your purposes, you can think of it as sort of a two-dimensional list. It's really a rectangular grid of numbers. Just stepping back for a second and aside, matrices are kind of the stars of what's known as linear algebra, which is about how you add, subtract, multiply, divide matrices. Matrices, if you go on other elements of science and engineering elsewhere, I suppose, you'll find that matrices are very nice little mathematical constructs that are really a labor-saving shorthand. But they're a little tricky at first to understand how to manipulate them, and your calculator is set up to do all those manipulations. You don't care. There's kind of almost no crossover between statistics and linear algebra. You are going to use matrices strictly as an input device for information in this test for independence. So we're not going to really spend much time on how the calculator is working, but we are going to work the calculator. So just before we do that, let's answer the first question, which is develop the null and alternative hypothesis. And as I've already said, the null hypothesis in test of independence is always the independence hypothesis. In this case, you would say voting preference and gender are independent. The antithesis, the alternative hypothesis, is that voting preference and gender are dependent. And that's the test you're running. You're really looking to see if this data, as it's laid out in the two-way contingency table, is close to an independent structure or not. And again, finding two numbers or two distributions are close is what hypothesis tests are all about. So this is another situation where if you were trying to do this problem you're doing with a calculator, you would have been done 5 minutes ago. So let's go ahead and turn the calculator on. Isn't that great? And let's execute this problem. So Calculator's on. I've jumped the gun a little bit. I have to go find a matrix to fill up. I do that by going second, matrix right there. And as if you were in stat, edit, and looking at lists, you are now in matrix, looking at a group of matrices that are available for you to fill up. 1, 2, 3, 4, 5, 6, 7, A, B, C, D, E, F, G. Let's just go to A, meaning let's toggle over to edit, tell the calculator we're there. And the first thing you have to do is tell the calculator what size or aspect ratio matrix you want. A matrix, rectangular grid of numbers, can be 1 by 1, 2 by 2, 2 rows, 2 columns, 3 rows, 3 columns. It can be 3 columns, 2 rows. There's no limit. You have to tell the calculator. And if I go back to the problem statement, I have got 2 rows, male, female, and 3 columns, Republican, Democrat, Independent. So this is a 2 by 3 matrix, okay? So let's go ahead and where that flashing cursor is, let's go tell it I've got a 2 number of rows and I've got a 3 number of columns, and look, it kind of lays out a 2 by 3 matrix for you. Believe it or not, we're almost done with the problem. So I have to input the data here. I go back to the problem statement and I'm just going to put the two-way contingency table in here. So this number is 200. The next number, the number of Democratic males here out of the 1,000 we looked at, is 150. The next number is 50. And watch the calculator just automatically sweep you down and look for the next number, 250. Next number is 300. Last number is 50. So I have just now put the observed data from the problem, 200, 150, 50, 250, 200. Oh, that's not 200, that's no, that is 300. I could go back here if I had written 200 and just type in 300 again. This works very much like the rows, the lists do elsewhere in stat edit. And actually, oh look, I did screw up that. I did screw up that last number. No, I didn't. It's 50. Yikes. Okay, so there we go. As I said, I'm almost done. I want to do an independence test. Okay, the tests are over here in stat tests. Let's swing down and look at chi-squared test. That's what we're looking for. It says, where is this observed matrix? You put it into A, it's all set up for A. It's now telling you it's going to calculate the expected matrix and it's going to throw it into matrix B. So if you do want to see the expected matrix, after we push the button to calculate here, it'll show up in B. So let me run down to calculate, lickety-split, there's the answer. Every time I do this problem, I get a slightly different answer, which is really a little bit concerning. I've gotten this one twice, I'm going to go with it. It says the p-value associated with this chi-squared value of 16 is 10 to the minus 4. So let's go write that over here. I'm really trying to do that right now. There's the p-value of 10 to the minus 4. Oh, by the way, note that it calculated the degrees of freedom. The degrees of freedom, remember, is 1 minus the row categories times 1 minus the column categories. 3 minus 1 is 2, 2 minus 1 is 1, 2 times 1 is 2. That's why the degrees of freedom shows up as 2. Okay, back to the problem at hand. The p-value is 10 to the minus 4. The level of significance is 0.005. The p-value is much smaller than the level of significance, and that means reject the null. And in our context, reject the null means that the survey provides evidence that voting preference depends on gender. You can see it if you look at it, actually. Okay. So that's much easier to do than it is to say again. You'll get a couple of these under your belt and you'll get bored of them pretty quickly. All right, talk again.